Good afternoon, everyone. So let us wait for 3 more minutes. We'll start the session by 3:05. So in the meantime, if there are people to join, they can join. Good afternoon, everyone. So I welcome you all once again to the Computational Fluid Dynamics course live interaction session. So we are now stepping into week 4. So the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Hyderabad. And while this live session is handled by myself, Ankara Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So I think professor is from IIT Madras, if at all I said wrong. Okay, now we'll move on. So we have seen the course layout. So this is a 12 weeks course with covering almost all the requirements for the computational fluid dynamics from the basics So till now we have seen the calculation of flow in a rectangular duct and calculation of fully developed flow in a triangular duct. Week 3 it was about derivations of equations governing fluid flow, and week 4 it is about equations for incompressible flow and boundary conditions, and week 5 it is basic concepts of CFD, finite difference approximation, and week 6 it is about consistency, stability, and convergence while doing that, and week 7 it is solution for Navier-Stokes equations for compressible flows, and week 8 it is Navier-Stokes equation solution for incompressible flows, and week 9 it is solution of linear algebraic equations basic methods, and week 10 solution of linear algebraic equations advanced methods, and week 11 and 12 it is about basics of finite volume method, grid generation, turbulent flows, and turbulence modeling. So now we have a basic understanding of fluid flow in a rectangular duct and triangular duct, and also what are the basic equations which are governing the fluid flow. So now we'll step into this week's problems. So this problem solving sessions are just to help you in solving the assignment problems or any other queries related to that. So this is in this class, in today's class we are having two cases, and then followed by that we have some questions associated with that. So we'll be solving problems based on those two cases and also some other generalized problems. So case 1 it is about a rectangular duct flow. So figure 1 it is about steady flow through a duct of a rectangular cross section with width W, height h and length L. So planes A and D are the inlet and outlet planes, while planes B and C are at a distance of 0.5 times of L and 0.9 times of L respectively. Normal velocity at inlet is uniform. Also, length is very much greater than W and length is very much greater than height. And one can expect the flow to have a fully developed by plane C. So what is given in this case is that first we need to understand what is given in the case. So it is mentioned that steady flow through a rectangular cross section with L and with W and height h. So we have a rectangular cross sectional plane. So this is height and this is width, and it is in y direction, it is in x direction. So and length is L. So in the z direction the length is given as L. So from this figure itself we are able to understand that length is very much larger than height and width. And we have four different planes. This is plane A, and this is plane B, and this is plane C and plane D. Just a minute, someone else is joining. So we have four different planes A, B, C and D. So before itself we have seen this is height h and this is W and this is length L. So length is very much greater than both height as well as the width of the duct. And we have four planes. So A plane is the inlet plane, that is V inlet. Fluid is flowing through the duct and it is entering the plane A with velocity V in, and it is leaving through plane D. So plane D is the outlet and plane A is the inlet, while planes B and C are in between the planes A and B. So plane B is at a distance of, is exactly at a half times of length. So if it is 1 meter, plane B is at a length of 0.5 meter or 0.5 times L, and plane C is at a distance of 0.9 times of L. So if it is 1 meter, it is at a 0.9 meter length respectively, length. So we have normal velocity at inlet is uniform and length is very much greater than width as well as height. So they are saying that fluid flow is fully developed by plane C. So by plane C, that is at a length of 0.9 L, the flow is fully developed. So this is what is given. So once again, so flow is fully developed by plane C, and plane D. So what are all the carry away from this case? First is steady flow is happening through a rectangular duct whose cross section is H and W, with W in X direction and height H in Y direction. So, height H and with W, and the rectangular plane is of length L, that is in the Z direction. So planes A and D are the inlet and the outlet planes, while planes B and C are at a distances of 0.5 and 0.9 L. So plane B is exactly at the midpoint. Plane C is closer to the outlet plane. So we are saying that by the time the fluid reaches the plane C, it is expected to have a fully developed flow. And planes A is normal velocity at inlet is uniform. So we will see the questions for this particular case. So question 1, it is asked that how many partial differential equations do we need to solve? So in general, when we are dealing with the fluid flow in some geometry, if we are neglecting all other things like reactions or heat transfer, if it is neglected, we have only we need to deal with only mass conservation and momentum conservation equations. So in terms of mass conservation, we have one continuity equation, and in terms of momentum conservation equations, we have three equations, that is in X direction, Y direction and Z direction. So in total we have four equations. So how many partial differential equations do we need to solve? We need to solve four partial differential equations in order to solve this particular geometry. So similar is this particular case. Here also we are solving the flow through a rectangular duct. So since we are dealing only with the fluid flow and not considering any other things that are happening inside the system, so we need to solve for four partial differential equations. So how many partial differential equations do we need to solve is the first question, and we have options. A is 1, B is 2, C is 3, 4, D is 4. So we know that the answer to this particular question is option D, which is 4. So what are the governing equations we need to be solving? First is the continuity equations, which can be written as dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0 when we are dealing with the incompressible fluid flow. And partial differential equations or momentum conservation equations, we have rho times of dou u by dou t plus u times of dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho gx plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. This is in x direction. And for y direction, we have rho dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou y plus rho gy and mu times of dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. And for the z direction, we have rho dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z is equal to minus dou p by dou z plus rho gz plus mu times of dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So these are the partial differential equations we need to be solving in order to understand or solve the particular system through CFD or through normal means. Also we need to solve the one continuity equations and three momentum conservation equations. So on the whole, we have four different partial differential equations which needed to be solved for this particular geometry or this particular fluid flow through a rectangular duct or anything. So we'll move on to question 2. In question 2, we have, if water is flowing through the duct and W is equal to 0.04 meter, H is equal to 0.03 meter and length is 1.5 meter, and inlet velocity for an inlet Reynolds number of 1000 would be about. So what is asked in this question? We have a rectangular duct. So if we assume water is flowing through this particular duct and with this 0.04 meter, H is 0.03 meter and length is given as 1.5 meter. So if the inlet Reynolds number is 1000, what would be the inlet velocity? So what is the formula for Reynolds number? Reynolds number formula is rho v d by mu. So we'll see the options quickly. Option A, it is 0.03 meter per second. Option B, it is 0.3 meter per second. Option C, it is 3 meter per second. Option D, it is 10 meter per second. So how should we solve this particular problem? We need to use the Reynolds number formula, that is RE is equal to rho V D by mu. So if it is a circular cross section, we can use direct substitution, that is diameter of the pipe can be substituted over there, and we can use the water properties, that is rho is 1000 and viscosity is 1.001. So if we use this, we can directly get the velocity values, which would be V is equal to 1000 times of mu by rho into D. So but in this particular case, we are having a rectangular cross-sectional duct. So when we are dealing with a rectangular cross-section, we need to go in a different approach to determine the diameter. So we'll just see, answer is option A, that is 0.03 meter per second. So we'll see how it is. So in question 2, let us first try the inlet given conditions. So W is given as 0.04 meter, H is 0.03 meter, length is 1.5 meter. So this particular rectangular cross section, we have 0.03 meter height and width is 0.04 meter. So first we need to determine the hydraulic radius of the system. So generally Reynolds number is rho V dH by mu. So here D for rectangular cross section is hydraulic radius. So right now we need to determine hydraulic diameter. So we need to determine how to find the hydraulic diameter of this particular rectangular cross sectional pipe. So dH is equal to 4 times of W into H, that is this width into height, and divided by 2 times of W plus H, that is the wetted perimeter. So this is wetted perimeter in 4 times of cross sectional area divided by the wetted perimeter. So 4 into W into H divided by 2 times of W plus H, that gives us the hydraulic diameter. So we are substituting the given values. So 4 by 2 becomes 2 and W is 0.04 meter and H is 0.03 meter, and W plus H becomes 0.04 plus 0.03, which is 0.07 meter. So we are substituting all the given in the above equation, where it becomes 2 into 0.04 into 0.03 divided by 0.07. So what answer we are getting? We are getting 0.03429 meter. And in this particular hydraulic diameter, now we should substitute back into the Reynolds equation. So Reynolds number is given as 1000 and Reynolds is equal to rho V dH by mu. So 1000 is equal to rho is 1000 for water, V is unknown, and dH is given as 0.03429 and it is 0.001 for the viscosity of the water. So in order to calculate this velocity, all other remaining terms go into that other side. So V is equal to 1000 gets cancelled. V is equal to 0.001 divided by 0.03429. So we are getting this particular V value as 0.0291, which is about 0.03 meter per second, which is what is asked in the question. So in the question it is asked that if water is flowing through the duct and W is equal to 0.04 meter, H is 0.03 meter and length is 1.5 meter, inlet velocity for an inlet Reynolds number of 1000 would be. So we have found out the answer is 0.03 meter per second. So this is how we found out. So first if we need to find the inlet velocity given the value of Reynolds number. So Reynolds number formula is rho V D by mu. So since it is a rectangular cross sectional pipe, we need to know the way to calculate the diameter. So we are using the hydraulic diameter. So this particular is found from this particular equation, where it is 4 into WH by 2 times of W plus H, and it is, on substituting the values, we get the value as 0.03429 meter, and after substitution back into the Reynolds number equation, we are getting the value of inlet velocity as 0.0291 meter per second, which is approximately equal to 0.03 meter per second. On rounding off, we get it as 0.03 meter per second. So I hope it is clear. Now we'll go to question 3. Question 3 is a similar question, but here instead of water as a fluid medium, we have a air. So it is mentioned that with reference to figure 1 is nothing but the case, what is given in this particular case. So with reference to figure 1, if W is equal to 0.04 meter and H is equal to 0.024 meter, length is 1.5 meter, inlet velocity of air whose density is 1.2 kg per meter cube and viscosity is 1.8 into 10 power minus 5 kg per meter second, for an inlet Reynolds number of 1000 would be about. So similar question, it is same as the last question, but here the fluid is a different medium. In the last problem we have seen the case where the fluid is water, but in this particular problem the fluid is air. So we have the density and viscosity values for air rather than water. So we have density of air is 1.2 kg per meter cube and viscosity of air is 1.8 into 10 power minus 5 kg per meter second. So similar to how we solved in the last problem, we need to solve this. So okay, let us first see the options given. Option A, it is 0.47 meter per second. Option B, it is 0.5 meter per second. Option C, it is 0.94 meter per second. Option D, it is 2 meter per second. So how are we going to solve? The answer to this is option B, 0.5 meter per second is the right answer. So similar to that, we'll solve this problem similar to how we solved in the last case. So we are first mentioning all the given conditions. So here the width is 0.04 meter and height is 0.024 meter. The height is different from the previous problem. Height was 0.03 in the last case, and now in this particular problem it is 0.024 meter. So and length is 1.5 meter, similar as to the last problem, and inlet velocity is needed to be calculated, and inlet Reynolds number is 1000. So first we need to identify the hydraulic diameter for substituting in the Reynolds number term. So Reynolds number is given by rho v dh by mu, and dh is nothing but 4 times of wh divided by 2 times of w plus h, and we substitute all the known values in this particular equation. So what are we getting? This particular 2 and 4 gets cancelled and we are left out with a single 2, and w is 0.04, h is 0.024, and w plus h is 0.04 plus 0.024, and after substitution we will be having the value as 0.03 meter. So hydraulic manometer we are found out as 0.03 meter. So if you have any confusions, you can I'll give you a half a minute time after this particular problem, so you can just see the calculation and just confirm if you want to recalculate it. So now we know the Reynolds number as 1000, and density of air is 1.2 kg per meter cube. V is unknown, and this is particular thing we have calculated as 0.03 and divided by viscosity of air, which is nothing but 1.8 into 10 power minus 5. So on substituting it and taking the all the known terms to the other side, we are having the V as 0.5 meter per second. So if you want to calculate it on your own, I'll just give a half a minute time. So just see that and we'll go to the next question. So what we have done is, it is a simple problem. We have just used Reynolds number formula as rho v d by mu, and d is unknown here because it is a rectangular cross-sectional duct, and for that we need to find the hydraulic diameter, and we have found out using this formula. And after that we have substituted all the known values in the Reynolds number formula, and we have found out the velocity at the inlet. So Reynolds number at the inlet is given and velocity at the inlet is as, and the fluid is given as air. So on the basis of that we have done our calculation, and we have found out the value, inlet velocity value as 0.5 meter per second. So yeah, I hope it is clear. We'll go to next question now. Question 4, it is asked that the continuity equation for this case can be written, sorry, the continuity equation for this case can be written as dou u by dou z plus dou v by dou z plus dou w by dou z is equal to 0. Dou u by dou y plus dou v by dou z plus dou w by dou x is equal to 0. Option C, it is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Option D, it is dou u by dou x plus dou u by dou y plus dou u by dou z is equal to 0. So on looking at the 4 equations, we can see that option C is the right answer, I guess. So this particular problem is the flow through a rectangular duct. So the continuity equation here, it is flow, incompressible flow is assumed, and on the basis of that we have the density term removed from the continuity equation. So what are we left with? We are left with del dot u is equal to 0, where u is a velocity vector. So del dot u is equal to 0 is the continuity equation, and u is the velocity vector. So on expansion, what we would be having, dou u by dou x, dou v by dou y, dou w by dou z. That is x component velocity with x, y component velocity with y, w component velocity with, sorry, z component velocity with z. And other term, so option C is the right answer. We'll just check it. Answer is option C. In other things, we can see that u is with z, v, like in all other things, we have taken a single things constant. Like here, everything is with respect to z. Here with even though it is with y, z, and x, everything is different, paired up different. Whereas option C is the only one which is done rightly. And so we'll go to question 5. In question 5, it is asked that the momentum balance equation in the x direction can be written as. Momentum balance equation in the x direction can be written as. So these problems are basically asking with regards to writing the partial differential equations, that is momentum equations, and the continuity equation, that is mass conservation and momentum conservation equations. So the first option is u times dou u by dou x, u times dou u by dou x plus v times dou v by dou y plus w times dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. Option B, it is u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. And option C, it is u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu times mu by rho times dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. And see option D, none of the above. So option C is the right answer. Yeah, because we can see that we are now asked to find the momentum balance equation in the x direction. So in momentum conservation equations, we have it in 3 directions. We have one equation for the x direction, one equation for the y direction, and one equation for the z direction. So of the 3 equations, we need to now identify which one is the correct one for the x directions. So from these options, if we look at it, option A, it is, although it is just a mix and match given u, v, and w, and actually if we look at right hand side, we can just discard this equation because it should have been u in all the equations, whereas here we are dealing with u here, v, y, and w. Similarly u, v, w, so both of them can be easily ignored, and option C is the right answer. We will just see how it is in the next slide. How many equations are given in the next slide? So yeah, this particular question, the question was about momentum balance equation in the x direction. Actually, we have seen the equations in particular slide, I think. Yeah, like continuity equation, momentum conservation equation, and the momentum equation in three directions, x, y, and z. So this is what is this particular equation. Okay, so x direction momentum equation was asked. So here it is the equation, but here is it, since it is a steady state, this particular term goes to 0, and this row we have taken to the other side. And I think gravitational force was assumed and neglected. So u times dou u by dou x plus v dou u by dou y plus w dou u by dou z. So now looking back into the equation, we have u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square, and therefore option C is the right answer. Now I would like to give a small thing about the governing equations and what is the significance of the terms present in the governing equations. So first we have now till now, if we consider, we have just dealt with four equations. That is one continuity equation and three momentum conservation equations. So in the first slide, let us see the continuity equation or the mass conservation equations. So the mass conservation equation in general appears as this: dou rho by dou t plus del dot rho v is equal to 0. So this is the original like vector form of the mass conservation equations. Dou rho by dou t plus del dot rho v is equal to 0. So what is the significance of term? So this is that the rate of change of density with respect to time. So how the mass is getting changed with respect to time inside the system. That is accounted in this particular term. I mean, from this particular term we have rate of change of density with respect to time, and this particular term is the convective term, which represents the mass change due to the fluid motion, like how like fluid flow affects the mass change inside the system. So this is given by convective term. So now we have rate of change of density with respect to time as well as the convective, that is the mass flow, how the mass flow, I mean fluid flow is affecting the mass change inside the system. So the continuity equation, significance of the terms in the continuity equation is that dou rho by dou t plus del dot rho v is equal to 0. It is a continuity equation which accounts the change with respect to time as well as the change with respect to the fluid flow motion. So this is a generalized mass conservation equation. So this is a generalized, as we have seen, this is a generalized mass conservation equation or the continuity equation. So if we are dealing with an incompressible fluid flow, that means density would not be changing. So at that time what we have is incompressible fluid, we have only del dot v is equal to 0. Remember that it is a vector form. So we are left with del dot v is equal to 0 when the fluid flow is incompressible fluid flow. So this is the continuity equations. Now let us move on to the momentum conservation equations. So momentum equation, we have rho dv by dt is equal to minus del p plus rho g plus mu del square v. So this is a vector form of the equation where v is the velocity vector. So it has u, v and w components if written in a separate form. So this particular term in the left hand side, we call it as a total derivative or substantial derivative, I guess. So this particular term is comprises of two different, it is a total derivative, so it includes effects from the total. So momentum conservation equation is in general a simple term which accounts mass into acceleration is equal to f. That is f is equal to ma. Newton's second law of motion is only accounted through these equations. So these are the moment mass into acceleration term, And this is the force terms like pressure gradient force, gravitational force, and viscous force. So all these terms, how it affects the momentum transfer within the system is accounted over here. And for this now we have so yeah, this particular term is the total derivative. Rho dv by dt is the total derivative. And now we have pressure gradient force, and these are this particular rho g is a body force. Some other force if required also would be included, so the generalized term is body force. And after that we have viscous force or the diffusion term. So that is how momentum change happening inside the system because of the diffusion and all. So this is the generalized momentum conservation equation, where we have F is equal to ma. Similar to that we have it. So this is rho dv by dt is equal to minus del p plus rho g plus mu del square v. So this is total derivative, this is pressure gradient, and this is body force, and this is diffusion term. And now if we look at total derivative, what we are having is, it is, as I said, it is comprising of two effects. The one is, if we expand it, we have rho times of d dou v by dou t plus v dot del v. So here it is change of velocity with respect to time, and this is the convective term. So what are we accounting here? It is accounting with change with respect to time as well as with the convective term. So if fluid is flowing, and because of the fluid flow motion, how the momentum conservation is affected, that effect is also included over here, and with respect to time how it is affected. So we have rho dv by dt is equal to minus del p plus rho g plus mu del square v. So it is, in the left hand side we have a total derivative, which is nothing but inclusion of the change of velocity with respect to time as well as the change due to the convective motion, which is accounted over here. And the right hand side we have all the forces acting, which is including pressure gradient force and body force and the viscous force, that is because that is including the diffusional effects. So how momentum transfer is occurring because based on the diffusion effects. So now we'll go to the actual some more problems. So since we were dealing with the continuity and the momentum conservation equations, I want to just give an idea about what those terms represent in reality. And in question 6 it is about an appropriate boundary condition at plane D is. So what is plane D? Plane D is the exit plane. That is, we have four planes, plane A, B, C and D. While A is the inlet plane, B is the mid of the whole plane, and C is very near to the exit plane, and D is the exit plane. So an appropriate boundary condition at plane D is: option 1, dou p by dou z is equal to 0. Option 2, it is dou w by dou z is equal to 0. And option 3, it is velocity is equal to velocity inlet. So we'll see the options also. Option A, it is 1. Option B, it is 2. Option C, it is 3. Option D, it is none of the 3. So if we are looking at plane D, the why the flow is happening? Flow is happening because of the pressure difference. Like it flows from like high pressure turns to the low pressure. So appropriate boundary condition at plane Z is, it is exit plane. So we cannot say that dou p by dou z is equal to 0. Dou p by dou z is not equal to 0. And option 2, it is dou w by dou z is equal to 0. So if you remember, it was mentioned in the first case that the flow has attained almost a steady state by plane C. So it has, if it is assumed to be reaching almost steady state, sorry, fully developed flow by the plane C, by C we can assure that it has reached. So if it is a fully developed flow, we can say that the flow would be uniform, and so dou w by dou z would be, I mean w would not be varying with z. So dou w by dou is z. That is, z is the flow plane. If you remember, so we have the rectangular duct like this. Just remember the length is very much greater, not like this. So this is z, and this is y, and this is x. So if we go with this, dou w by dou z is equal to 0. This is the boundary condition that we can apply at the exit plane D, because we have seen that by plane C the flow has attained a fully developed condition. So answer to this particular problem is option B, that is 2 is the right answer. We'll just check if it is right. Answer is option B. Option B is the right answer. Now we'll go to question 7. Flow is fully developed by plane C. So after that it would be dou W by dou Z is equal to 0. In question 7 it is asked that, okay, you find that your company's air to air heat exchanger is not performing well. Okay, air to air heat exchanger is not performing well as the one offered by a competitor. Your boss thinks this is because the flow is not distributed well on the cold side and would like you to see if this is the case by doing a CFD simulations. Okay. Your boss thinks this is because the flow is not distributed well on the cold side and would like you to see if this is the case by doing a CFD simulations. What would your response be? So what is the case here? There is an air-to-air heat exchanger in your company which is not performing very well because it is offered by a competitor. So your boss is offering a case study, like you the position to do this and find out if it is the case because flow is not distributed well on the cold side, and he is asking you to check it by doing a CFD simulations. So what would the response be? It is basically asking whether CFD can be used in such cases or not. So option A, it is you assure your boss that using CFD one can readily verify if the suspicion is justified. Option B, you express your doubt about the accuracy of the CFD given the complexity of geometry, turbulence, etc. And option C, it is you suggest that an analytical approach is more suitable than CFD. You would rather do experiments. So we'll just look at the options given. So the first option is given that it is asking you assure your boss that using CFD one can easily readily verify if the suspicion is justified. This is true because it is an air-to-air heat exchanger. So we can just study it using CFD, and it is just we can see that if the flow is distributed well on the cold side or not by doing a CFD simulations, which is pretty much doable. So we can assure our boss that using CFD we can easily verify if the suspicion is justified. So we can use, we can say that if that particular claim is true or false by doing a CFD simulations, and we can say that if the flow is distributed well or not, or if any other things are causing that we can be further dealt with. So initially we can say that if the suspicion is true or false by using a CFD simulation, that the flow is if the flow is distributed on the cold side properly or not. So option A is true. Option B, it is given that you express doubt about the accuracy of the CFD given the complexity of geometry, turbulence, etc. So what it is said that we are expressing the doubt about the accuracy of CFD given the complexity of geometry, turbulence, etc. So basically CFD can be used in cases where geometry is complex, and we can also account the turbulence effect. So all these things would not affect the accuracy of any particular problem we are dealing with in the CFD. So we need not express our doubt regarding the accuracy of CFD given the complexity of geometry, turbulence, etc. So even though the geometry might be complex or turbulence effects are included, we can get a pretty much accurate results from the CFD. Option C, you suggest that an analytical approach is more suitable than CFD. Analytical approach is not at all possible in these cases because like solving those many equations analytically, if it had been possible, it would have been done rather than going with the CFD studies, because we are imagine we are having one continuity equation and three momentum conservation equations, and since it is an heat exchanger we would be dealing with energy conservation equations as well. So basically it is not practically doable. So option C is false. Option D, you would rather do experiments. Yeah, like what if it is initially we are going with CFD because we need a solution and doing experiments and finding out if it is right or wrong. Like we are putting forth the claim and it, like with CFD we can get a simulation, I mean results from the system itself. But imagine doing an experiment and it would be very much tedious, so we would not prefer to do the experiments. So option D is false. So answer to this particular question is option A. You assure your boss that using CFD one can readily verify if the suspicion is justified. And now we'll also go to question 8. In question 8 it is asked that a client has produced a new catalyst that improves the rate of a catalytic chemical reaction and wants you to determine through CFD simulations how much better yield it would give compared to old catalyst. What would your response be? Option A, you expect CFD to give you a reasonably correct solution. Option B, you expect CFD would not be of much use because flows with catalytic chemical reactions cannot be handled through CFD. Option C, you think CFD would be used but it would not be practical as flow over and through each catalyst practice particle would not be you think CFD would be used but it would not be practical as flow over and through each catalyst particle would need to be simulated. You expect CFD would be of use in establishing the relative goodness of new catalyst. So what is asked? A client has produced a new catalyst that is said to improve the rate of the chemical reaction and they are giving it to us to determine the through CFD simulations how much better yield it would give compared to the old catalyst. So we are now having two catalysts. One is old catalyst, one is a new catalyst. So through CFD simulations, is it possible to determine uh, how much better yield it is giving compared to the old catalyst? It is very much doable. So option A, you expect CFD to give you a reasonably correct solution. Uh, Obviously we expect CFD to be give us a reasonably correct solution. So option A is considerable. Option B, it is given that you expect CFD would not be of much use because flows with catalytic chemical reactions cannot be handled through CFD. What it is given? Uh, uh, in this particular case, we are having a chemical reaction and catalyst involved. So we are thinking that it would not be of much use because we are dealing with a complex things like catalytic chemical reactions and handling it through CFD is a difficult. But in reality, it is not the case. CFD has improved so much that it is now possible to simulate the catalytic chemical reactions also. So option B is false. And option C, you think CFD would be used, but it would not be practical as flow over and through each catalyst particle need to be simulated. Again, this is false because if we know the system geometry and what system is doing, it is very much doable because we know the catalyst rate and we can use the mass conservation, momentum conservation, species balance equations and also energy conservation equations. So almost like the 8 or so equations would be coming and on solving that we can obtain a reasonably better results than doing it through experiments also. So we can say that it is very much practical because we are now only dealing with one governing equation, three momentum conservation equations, and like we will be having species conservation equations and energy conservation equation. Energy conservation equation is would be one and species conservation equation it would be depending on what type of system. If there are like 5 or 6, it would be coming out 6 minus 1 or 5 minus 1 because already we are dealing with the continuity equations. So in that case 1 plus 3 plus 1 4 5 equations where 1 is continuity, 3 momentum conservation equations and 1 energy conservation equations plus additionally the number of species minus 1 equation. So solving those many equations is practically feasible. So it is option C is false. Option D, here it is mentioned that you expect CFD would be of use in establishing the relative goodness of the new catalyst. So option D is the right answer where it is given that we expect CFD would be of use in establishing the relative goodness of the new catalyst. So we can say that new catalyst is better than catalyst or not, and we can say how much, if it is better, how much better yield it is giving compared to the new catalyst. So this is question 8, and now we'll go on to question 9. Okay, option D is the right answer. Option D, that is, you expect CFD would be of use in establishing the relative goodness of new catalyst. Now we'll go to question 9. In question 9, what it is asked, your friend who is a clinician working at a large teaching hospital and is thus engaged in research wants to collaborate with you in simulating the effect of coronavirus on the lungs and breathlessness that is associated with it. What would your response be? Okay, what is given? Your friend who is a clinician working at a large teaching hospital and is thus engaged in research, and they want to collaborate with us in simulating the effect of coronavirus on the lungs and breathlessness that is associated with it. So what is given? Option A, let's go ahead with it. It is not too difficult. Option B, it is not that straightforward, but I'm sure we can get it right, and therefore let us go ahead with it. Option C, it is pretty difficult and it won't probably be useful for this coronavirus, but let us go ahead with it anyway. Option D, count me out, I have better ways of spending my time. So, what is it asking? So our friend is a clinician and it is working at a very large hospital, and they want to collaborate with us to understand the effect of coronavirus on lungs and breathlessness that is associated with it. So in that situation, what would our response be? So basically, there are very so many efforts were made using CFDs during the pandemic to study this. Like it was used to understand the dispersion and transmission in different situations, like in buildings also, how it is dispersing and how it is dealing with, it was studied. And like how it can be transmitted from person to person, and those things were studied. Like, but in this particular case, the question is about how it would be affecting the inside the lungs and breathlessness that is associated with it. So this particular thing is a pretty difficult one, so we cannot say how it would be affecting. So for example, if you can go to the literature, you can very much see that how CFD studies were used during the pandemic time and studied. So it was mostly studied with airborne dispersion, not within the human like in lungs, or how breathlessness it is associating with it. So it is pretty much difficult, and it is not probably useful to use CFD to study this particular coronavirus, but we can go ahead and try with it. Like, we can see what it is giving out the results, because we should not be ruling out anything. So we can just try and get something, and we can see how it is useful. But option A, it is, let's go ahead with it. It is not too difficult. It is false because it is quite complex. And option B, it is not that straightforward, but I'm sure we can get it right, and therefore let us go ahead with it. Even that is not true, because we are not sure what we would be getting. Option C, it is pretty difficult and it won't probably be useful for this coronavirus, but let us go ahead with it. I think it is option C, because it is quite difficult and the results may not be useful, but still we can give it a try. And option D, count me out, I have better taste. This is not a better option. So option C is a better one when we are dealing with CFD studies, so I should give it a try. So answer is option C. Like once we give it a try, we can say that how useful it is or how difficult it is, but it is a difficult thing. Now we'll go to question 10. In question 10, which of the following statements is true about velocity at the midpoint of plane B? Plane B is at the midpoint between planes A and D. So it is exactly at the mid of the rectangular duct. So option 1, it is W velocity is greater than V inlet. Dou W by dou Z is equal to 0. Dou W by dou Z is equal to constant. Okay. Option A, it is 1. Option B, it is 2. Option C, it is 3. Option D, it is none of the 3. So answer is option 1, because uh, when the fluid is flowing through the rectangular duct, the velocity is increasing. So we can say the W velocity is greater than V inlet. So it is, the velocity is more than how it has started. So velocity is greater than V inlet. Option 1 is, statement 1 is true. Whereas in statement 2 it is mentioned that dou W by dou Z is equal to 0. It is false, because um, plane B is at the midpoint of planes A and D. It is not exactly at the uh, fully developed regime. So it is in the entrance region or in the zone where the flow is still developing. So dou W by dou Z is not 0 at that particular point, and dou W by dou Z is again not constant, because velocity is increasing. We cannot say that it is a constant one. So option 1 is the right answer, which is given from A, that is 1 is the right statement. We'll see the answer. Answer, it is option A. We'll go to question 11. In question 11, it is given that which of the following statements is, I think, we'll let us just take a 5 minutes break. Now the time is 3:58. We'll come back by 4:03 and then we'll start. Yeah. Like, we'll take a 5 minutes break. We'll join the session again by 4:03. Thank you. Uh, yeah, I will just start. Just a moment, just give me a minute. So yeah, we will just start now. Sorry. Which of the following statements is true? So yeah, we'll start now. Which of the following statements is true for a Newtonian fluid? Viscous stress versus strain relation is linear. Viscous stress is proportional to the local deformation rate. Statement 3, viscosity is independent of shear stress. So option A it is 1 and 2. Option B it is 2 and 3. Option C it is 1 and 3. Option D it is 1, 2 and 3. So the question is regarding Newtonian fluid. Newtonian fluids are nothing but they have those that obey the Newton's law of viscosity. So in those laws, the shear stress is directly proportional to the shear rate. So here it is given that option 1 it is viscous stress versus strain relation is linear. It is false because it is proportional. Viscous stress versus viscous strain. Viscous stress versus strain rate is linear, but strain is not linear. And it is option statement 2 it is viscous stress is proportional to the local deformation rate. It is true because stress is proportional to the deformation rate. And statement 3 it is viscosity is independent of stress. Again this is true because we are now the question is about Newtonian fluid. In Newtonian fluid, viscosity does not depend on how much stress we are offering or how the stress we are giving does not influence the behavior or the viscosity of the fluid. That is true for the Newtonian fluid. So statements 2 and 3 are right, which is given from option A it is 1 and 2. False. Option B it is 2 and 3. It is right. Option C it is 1 and 3. And option D it is 1, 2 and 3. So right answer is option B. 2 and 3 is the right answer. And we are dealing with the Newtonian fluid. Newtonian fluid viscous stress versus strain rate is proportional and it is independent of the shear stress. That is viscosity is independent of the shear stress. So now we'll go to question 12. In question 12, for a fully developed flow, the steady state momentum balance equation reduces to dou square W by dou y square is equal to 0. Dou square W by dou x square plus dou square W by dou y square is equal to 0. Option C it is dou square U by dou x square plus dou square V by dou y square is equal to 0. None of the three. So first we need to see this particular domain and in which consider this is very large. I have written very small one. So this is Z direction, this is Y direction, this is V, this is W. So the flow is happening in the Z direction, that is flow is happening in this particular direction. So the velocity would be W component velocity. So here W component velocity would be a function of X and Y for the fully developed flow, because we have seen dou W by dou Z is equal to 0. For the fully developed flow, in the plane D, we have seen that dou W by dou Z is equal to 0 because it is attained a fully developed state and it is a steady state. So what is the momentum balance equation reduces to? So from this we can see that W is a function of X and Y. So option A it is given dou square W by dou Y square is equal to 0. It is false. Dou square W by dou X square is equal to plus dou square W by dou Y square is equal to 0. Actually here thing is dou square W by dou X square plus dou square W by dou Y square is the terms would be remaining, but it would not be zero. It would be a constant, or pressure gradient would be there, so it was not equal to zero. So on that basis we are ruling out option B as well. Option C, it is dou square u by dou x square plus dou square v by dou y square. Again, it is not the case. So steady state momentum balance equation does not reduce to this. So this as well is false, and option D, it is none of the three is the right answer, because dou square w by dou x square plus dou square w by dou y square would be equal to pressure gradient, that is dou p by dou z. So that would be a constant, it would not be zero. On that basis we are ruling out B, and all other remaining things, option A and option B, are wrong. So answer to this particular problem is none of the three is the right answer. Answer is option D. Now a similar question, I think it is in the question 13, where it is given that instead of the same thing, we are just going to see how the fully developed equation looks like. For a fully developed flow, the steady state momentum balance equation reduces to dou square w by dou x square plus dou square w by dou y square is equal to constant. Dou square w by dou x square plus dou square w by dou y square is equal to 0. Dou square w by dou z square is equal to 0. Dou square w by dou z square is equal to constant. So the option B we have seen in the last slide itself how it is wrong, because it is equated to 0, but in reality it would not be 0, it would be equal to a constant value. So option A is the right answer. Dou square w by dou x square plus dou square w by dou y square is equal to some constant. So answer is option A. So maybe we can just go to the equations and look once. So momentum conservation equations, we have seen that W would be a function of x and y for the fully developed condition. Fully developed condition, it would be a function of x and y. So it would not be 0. So w by dou t, since it is a steady state, that would be becoming 0. And w is not a function of, I mean, u velocity is 0 and v velocity is 0, and w velocity is not a function of z for a fully developed state. So left hand side becomes 0, and dou p by dou z remains, but for a fully developed flow there will be constant, and rho g z is remaining. And this, from this terms, dou square w by dou x square is there, dou square w by dou y square is equal to there, and dou square w by dou z square is vanishing. So these terms are remaining, and if we take these all these terms on the other side, we will be left with some terms. So that we are saying dou square w by dou x square plus dou square w by dou y square is equal to constant. They are not equal to 0. So that is what we have seen in question 12 and 13. So in question 12 it was given 0, which is wrong. So answer is none of the three. Whereas in question 13 it is given as a constant, which is the right answer. So answer to this particular question 13 is option A. Dou square w by dou x square plus dou square w by dou y square is equal to some constant value. So answer is option A. Now we will go to question 14. In question 14 it is asked that which of the following statements is true about Newtonian fluids. So now we need to identify which of the following statements is true regarding the Newtonian fluids. So previously itself we saw that Newtonian fluids are those that obey the Newton's law of viscosity. And first statement it is given, Newtonian fluid is an idealization. No real fluid comes close to satisfying the assumptions. So this particular thing, if we see that it is a false, because Newton's law of viscosity is obeyed by almost all the fluids that we know, like water and some chemicals. So almost most of the things that we know in fluid would be obeying the Newton's law of viscosity, that is shear stress is proportional to the shear rate, and shear stress would be, I mean, viscosity would be constant at that particular temperature. So Newton's fluid is an idealization is a false statement. No real fluid comes close to satisfying the assumptions, which is a false, because there are many fluids which are satisfying these assumptions, and it is not an ideal case. And of statement 2 it is that many real fluids are Newtonian. This is true because many real fluids that we know are Newtonian fluids, like water and chemicals. Most of the chemicals, air, everything are Newtonian fluids. And for statement 3, it is for non-Newtonian fluids, Navier-Stokes equations are not applicable. This is true because in Navier-Stokes equations, we have dealing with the shear stress, viscous stress, force, and based on that how momentum terms are getting affected. So right now the shear stress, how it is affecting the things are not put over there. Their viscosity is assumed as a constant. If it is not, Navier-Stokes equation is not applicable. So that case, for non-Newtonian fluids, Navier-Stokes equations are not applicable is a true statement. So of the three statements, which of the following are right? Statement 2 and statement 3 are right. So we'll see the options. Option A, 1 only. Option B, it is 2 only. Option C, it is 1 and 3. Option D, it is 2 and 3. So from our understanding, what is true? It is 2 and 3 are the right answers. So which is given from option D. That is meaning it is saying that second and third statements are right. Second and third statements are stating that many real fluids are Newtonian fluids, and for non-Newtonian fluids, Navier-Stokes equations are not applicable, which is true. First statement is wrong because it is saying that Newtonian fluid is an idealization, which is not, because most of the fluids that we see in our day-to-day life would be coming closer to the Newtonian fluid and satisfying those assumptions, which is that shear stress is proportional to the shear rate or the local deformation rate, and viscosity would be almost independent of this shear stress. So option D is the right answer. 2 and 3. 2 and 3 are right. So now we'll see how we are classifying, how the classification of the fluid into Newtonian and non-Newtonian. So fluid types basically comes under Newtonian and non-Newtonian fluids. So we have said that it is like basis on shear stress and shear rate, right? So we will see a plot with shear stress versus shear rate. So the first is a Newtonian fluid, which is stating that shear stress is directly proportional to the shear rate. So we can say that Newtonian fluid, which is a straight line, directly proportional line. And one such example for the Newtonian fluid is water. Water is an example of Newtonian fluid. So we are here where we are stating the shear stress is proportional to the shear rate. And next type of fluid is the pseudoplastic fluids. They come under the shear thinning fluid. So if we give the shear stress, the viscosity would be reducing. So when we are giving the stress, the viscosity is said to have been reduced. For example, in ketchup and all, if we apply more shear or more stress, the viscosity we can say would be reducing. So those comes under shear thinning fluids, or we call it pseudoplastic. The one example for that is ketchup. And next is category is we have dilatant fluids or shear thickening fluids. We have a cornstarch in water as an example, because what happens is that when shear stress is applied, the viscosity is found to be increasing. So for example, mix up a cornstarch in water, and when you keep on mixing, you can find that it would be thickening, like viscosity would be increasing, and it would be difficult to mix at one point, because when you keep on stressing it, the viscosity has increased. Similar case you can observe in quicksand also. Like when the movement is more, it would be like very much difficult to pull out, like viscosity would be seemingly increasing. So another category is that Bingham plastic, and example for that is toothpaste. So here it is say like shear stress is proportional to shear rate, but for that we initially some amount of stress is required, like we call it yield stress. So if initial stress is put in the fluid, after that the fluid starts behaving in a such like similar to the Newtonian fluid, and we call it Bingham plastic. For example, toothpaste and all, like initially we would be giving out some yield stress in the form of pressing. After that the fluid flow starts to happen, but before that the fluid flow would not be happening. So for that case we need an initial amount of stress which would be further assisting in the fluid motion. Like that initial stress would aid, and after that the shear stress and shear rate would be linear, like the relation would be linear. So that is the Bingham plastic. So these are the broad classification of the Newtonian new fluid based on the Newton's law of viscosity. And like here again some more things come, like rheopectic, I'm not sure, I don't remember exactly now. That would be like how it is changing with respect to time, whether it is increasing or decreasing. So those things are not coming. So this is just to give an idea, because we have seen few problems based on Newtonian's fluid and non-Newtonian fluid. So since we know now that, see here, shear stress is not directly proportional to shear rate for the non-Newtonian fluids. All these three, Bingham plastic, shear, pseudoplastic and dilatant, comes under the non-Newtonian fluids. So shear stress is not proportional to shear rate and the viscosity would be a complex relation. So using Navier-Stokes equation to solve these is uh, not possible. So no, for non-Newtonian fluids, Navier-Stokes equation is not applicable. So that is what we have seen in this particular slide. Non-Newtonian fluids, Navier-Stokes equations are not applicable. Real fluids, many real fluids are Newtonian. One example is that water, and so many chemicals we can see, and so many things that we look at in real life would be coming under Newtonian fluids. So Newton's fluid is not an idealization. Many real fluids comes close to satisfying the assumption. So option 1 is, I mean, first statement is wrong, 2 and 3 are right. So on that basis we go with option D. Go to question 15. In question 15, which of the following statements is true about incompressible flows? Statement 1, it is incompressible fluid. Incompressible is only an idealization. No real flow is incompressible. Statement 2, incompressible flow is a very good approximation for many real flows. Navier-Stokes equations are not applicable for compressible flows. Okay. When we look at it, incompressible fluids, what we say, when there is no change in density, we call it incompressible flows. So normal flows would almost comes under the incompressible fluid flow cases. So the first one is incompressible is only an idealization. No real flow is incompressible. It is false, because it is not an idealization. Many cases that we see in our daily life would be an incompressible flow. And second statement is incompressible flow is a very good approximation for many real flows. So this is true because when we are dealing with CFD, if it is an incompressible fluid flow problems, that would be easier to solve. So many flows, if the density change is negligible, we classify it as an incompressible flow. So there is, we can say that it is a very good approximation for many real flows. Statement 3, it is stating that Navier-Stokes equations are not applicable for compressible flows. This is false, because we can use Navier-Stokes equations for compressible flows because already there are existing terms for density as well. If the fluid flow is incompressible, we can simplify those equations, but the original equations are just applicable for all types of flows. So incompressibility is a simplification, whereas compressible flows can be solved anytime. So we'll see the options. Option A, 1, false. Option B, 2. Option C, 3. Okay, I think okay. Yeah, second statement alone is right, because the third statement, it is given, are not applicable for compressible flows. This is false because it is applicable. So as we have mentioned that Navier-Stokes equations are applicable for compressible flows, because incompressibility is a simplification, whereas the originality is for compressible, I mean all types of fluids. So the first one is 1, it is false because incompressibility is not an idealization. Real flows, it can be incompressible too. Second statement is true because incompressible flow is a very good approximation because it reduces the calculation When there is like a negligible amount of density changes, we can classify it as an incompressible fluid flow. Therefore, second statement is right, and third, it is given or not applicable, which is false because they are applicable. So option A it is 1, option B is the right because second statement is the only right statement here, and 3 is C is 3 and D is 1 and 3. Option B is the right answer. Question 16. Which of the following assumptions is necessary in CFD simulation of a fluid flow problem using Navier-Stokes equation? So when we are dealing with CFD simulations of a fluid flow problem in a particular geometry, which of the assumptions are necessary? Option A, it is laminar flow. Option 2, it is boundary layer flow. Option 3, it is fully developed flow. Actually, which of the following assumptions are necessary? In my opinion, none of these assumptions are necessary. We'll just check the answer once. For none of the three is the right answer, because consider a domain fluid flow geometry problem where we are dealing with fluid flow. Like the flow can be laminar or turbulent, it can be anything. So do we need to consider all the flows as laminar? Because only then we can solve it. It is not that case, because this assumption is not necessary. The fluid can be laminar flow or turbulent flow. Whichever the case, we can use Navier-Stokes equations to solve it. It is just a momentum conservation equation. So laminar flow or turbulent flow, like further cases would be coming up. I mean, for like in solving turbulent flows, the things would be complex, but that doesn't mean that we need to assume all the flows as laminar. So this is a false. And boundary layer flow, and it would be like having certain percent of the assuming some assumptions as of having a boundary layer, like that much percentage of thing is reached over here. That assumption is not again required, because here we are saying that if a particular variable has reached this particular values, some assumptions would be there. It is a simplification of Navier-Stokes equation. That is, boundary layer approximation is there actually, but it is not a basic case. So in basic case, we can go with solving to laminar or turbulent or any type of flows. So boundary layer flow is one approximation which deals with few cases. But in the generalized case, we need not make this assumption. Like this assumption is not required. And fully developed flow, imagine the fluid flow would be attaining fully developed flow after some region. That is not required, because then we can say that like the solution would be only in that region. What about the initial region where the flow is still developing? So if that is the case, then it is not required to go with this approach at all, because it is not giving you the true values. So all three are false. So answer to this is none of the three is the right answer. So 1, 1 and 2, like all the options are wrong. Okay, now we are now moving on to case 2. Case 2 is this particular domain where it is like x, y and z. Yeah, this is a rectangular thing. We'll see what is given. Case is, we need to solve for the fluid flow in a reactor in which carbon monoxide is getting converted into carbon dioxide with the production of hydrogen, water gas shift reaction on a catalyst. Carbon monoxide plus water, it is giving carbon dioxide plus hydrogen over a catalyst. And okay, let us assume a simple configuration for this reactor. The multi-gas mixture flows through a rectangular channel. Due to its reaction, its composition changes from inlet to the outlet. The top and bottom walls of the channel are coated with the catalyst, and the two sides are used to heat up the gas to the desired temperature of 200 degrees Celsius. For a given flow rate of air of the given concentration of 4 gases, for given side wall heat flux and given catalyst surface area, we wish to calculate the percent conversion of CO to CO2 by the time it reaches the end of the channel. We want to find this out using CFD simulations. Assuming steady laminar flow and first order reaction kinetics for the reaction, answer the following questions. So what is given? Actually, in that particular thing itself, we have seen a rectangular channel. just for our understanding, we'll do this. We need to solve for the flow in a reactor in which carbon monoxide is getting converted to carbon dioxide. So this is the reaction that it is happening inside this particular reactor, where carbon monoxide plus water is giving carbon dioxide and hydrogen over a catalyst. So here we are using a simple configuration for this reactor. Multi-gas mixture, that is we are having carbon monoxide along with something and plus water, and this is passed through a rectangular channel, and due to its reaction its composition changes from the inlet to outlet. So let us keep this inlet and let us keep this outlet. So this multi-gas mixture is flowing from here to there, and from because of the reaction it is changing its composition from inlet to outlet. The top and bottom walls are coated with catalyst. So what they are saying, uh, this top and similar bottom is coated with catalyst, and two side walls, that is this wall and the opposite side walls, are used to heat up to the so we are providing heat source over here to 200 degrees Celsius for a given flow rate of air with a given concentration of four gases. For a given side wall heat flux and given catalyst surface area, we wish to calculate the percent conversion from CO to CO2 by the time it reaches the end of the channel length. So what is given is that basically we have a rectangular channel through which we are passing an inlet gas, and at the outlet we are getting some throughout the channel we are some reaction is happening, because top and bottom portion is coated with the catalyst and left and right wall we are providing a heat source. So if for a given flow rate of air, we have concentration of four gases, and like heat flux is also there because we are providing a heat source, and we have provided the catalyst and catalyst surface area. So what is the conversion from carbon monoxide to carbon dioxide that needs to be calculated by the time it reaches the channel length end. So this needs to be calculated using a CFD simulations. So what are the assumptions we are making? We are making steady laminar flow and first order reaction kinetics. So from this basis we need to answer the following questions. So the question 1, it is mentioning that, I hope this case is clear. Now we'll deal with the questions. In question 1 it is given that which of the following needs to be specified for statements is true. Which of the following needs to be specified for statements is true about the chemical reaction? So in four things are given over here, and it is mentioned that these needs to be specified for studying the chemical reaction inside the system. So which of the following mentioned over here is true about the chemical reaction? So the following needs to be specified is for statements is true. So the four statements are like needs to be specified. So we'll see that first one is rate of reaction, reaction kinetics, heat of reaction. Okay, sorry, if not 4, 3. So for studying the chemical reaction, it is mentioned that these three things needs to be specified. Like reaction, rate of reaction needs to be specified, reaction kinetics needs to be specified, and heat of reaction needs to be specified. So which of the following statements, that is needs to be specified statements, is true about the chemical reaction? First is rate of reaction, reaction kinetics, heat of reaction. Option A 1 only, option B it is 2 only, option C it is 1 and 3, option D it is 2 and 3. So actually what we need to know is reaction kinetics and heat of reaction. I guess it is option D is the right answer. I'll just check. Yeah, option D is the right answer, because from the reaction kinetics we get to know so many things like how it is happening and how things are happening inside the system. So we need to know the reaction kinetics. Reaction kinetics meaning stoichiometric coefficients, order of the reaction, constants in rate equation. So from these things, rate of reaction doesn't affect if we know all the things. So if we need to calculate the chemical reaction, what needs to be specified is that reaction kinetics. Reaction kinetics meaning we need to know the stoichiometric coefficients, order of reactions, and constants in rate equations if any are there. So these give us an idea about what is happening inside the system in terms of chemical reaction, or due to like species, how it is, like if we know these reaction kinetics only, then we can say that this particular reaction is happening, and because of that we get to know how it is producing, how much it is converting, everything would be get to know. And heat of reaction, So we also need to know the heat of reaction, because we are also like this would be affecting the source term in the conservation equations, that is the governing equation. We need to know the heat of reaction, because this would be affecting the temperature inside the system. So based on that, like it would be either consuming the heat or taking, like giving up the heat. So that energy balance equation needs to be would be significantly affected on this basis. So it is required to know the reaction kinetics and heat of reaction, that is second and third statement is need to be known. So our answer is option D. We'll go to question 2. In question 2 it is mentioned that which of the following do we need to specify about the catalytic reaction. Sorry. So which of the following do we need to specify about the catalytic reaction? So first is activation energy, second is catalyst surface area, third is order of the reaction, and fourth is reaction mechanism. So if we are going with this, 1, 2 and 3 are right. So we'll just check. Answer is, options are 1 only, B 1 and 2, C 1, 2 and 3, D 1, 2, 3 and 4. Answer is option C. Because in previous slide itself we have seen we need to know the reaction kinetics. So reaction kinetics gives us an idea about the activation energy, order of the reaction, everything. And so we need to know the catalytic reaction. When we are dealing with, we need to know the reaction kinetics and heat of the reaction. That's what we have seen in the last slide. So reaction kinetics includes the terms about activation energy, order of the reaction and everything. And also we need to know the catalyst surface area, so that we can get an idea about how much surface area it is having for the reaction. So these things needs to be known. Reaction mechanism, like it can follow different parts of the path for converting from the products, sorry, reactants to the products. So it need not be known. We need to know only the overall things, like this is getting converted to that, and what is the order of the reaction, and what is the stoichiometric coefficient of that equation, and what is activation energy, if any, for that particular thing. So these things we need to know. So answer is 1, 2 and 3. That is activation energy, catalyst surface area and order of the reaction. So answer to this particular question is option C, that is 1, 2 and 3. We'll go to question 3. In question 3 it is asked that how many mass conservation equations do we need to solve? Option A only 1, option B it is 2, option C it is 3, option D it is 4. So previously we have not included any species balance equations in the fluid flow problem, but in this particular fluid flow problem we have considering, in addition to the mass and the momentum conservation equations, here we are considering the chemical reaction. So this particular chemical reaction, we are giving a reactant, giving the reactants and getting the products. So along with that we are supplying the heat source also. So the number of equations in generally needs to be, it would be like including mass conservation equation, momentum conservation equation and species balance equations, because it is a reaction happening. We will be having reactants and the products. So how much reactant is in the inlet and how much reactant is in the outlet. So that species balance equation, species conservation equations and finally energy conservation equations. So how many species conservation equations we would be solving? It would be depending on the number of components present in the system. Like in this particular problem we are having 4. For example, this particular thing, we have carbon monoxide reacts with water and it gives carbon dioxide and hydrogen. So carbon monoxide is there, H2O is there, CO2 is there and H2 is there. So we are having 4 gases. So for a given flow rate of air with a given concentration of 4 gases, we are solving this problem. So we have 4 species. So on basis of species conservation equation, we have to solve for 4. But uh, on the basis of degrees of freedom, if we look, we are already solving a one mass conservation equation, that is continuity equations. So here we would be having one equation from there also. So like if we take into account that, we can subtract one species conservation equation, that is 4 minus 1. Like CO plus H2O giving H2 plus CO2, we have 4 species, but from continuity equation we have 1. So totally there are 5 mass conservation equations, but since we are accounting a continuity equation entirely, we can subtract 1 on the basis of the degrees of freedom. So number of species would be 4 minus 1, that is 3. So like if we add all the 4 equations, we would be getting the total mass conservation equation, which is accounted in the continuity equation. So we are subtracting 1 and from the species conservation equation, because we are already accounting it in the continuity equations. So like because if we solve for 4, the total would be again the same, right? So there is no point in solving. And the total number of mass conservation equation therefore becomes 3 species balance equations and 1 continuity equation. So 1 plus 3, that is giving us 4. 4, like number of species also we can say, that is 3 plus 1, it would be 4. So but behind the things, what is happening is that we have 1 continuity equations and 3 species balance equations. So total number of equations is 4. 3 plus 1. So we'll go to question 4. In question 4, it is asked that assuming the flow to be 3-dimensional, the total number of partial differential equations that need to be solved is 5. Option B, it is 6. Option C, it is 7. Option D, it is 8. So right now what we are doing, we are having a rectangular channel where we are passing the reactant gas and we are getting our product gases, and simultaneously it is coated with the catalyst on the top and the bottom, and in the left and right walls we have the heat source. So on the whole we have mass balance, momentum balance, species balance and energy balance. If we need to do to completely get a picture of what is happening inside this particular system. So in all these balances, how many equations do we need to solve? That is coming. So in continuity equations, we have one equation, and in momentum conservation equation, since it is a 3-dimensional problem, we have x momentum, y momentum, z momentum, 3 equations. So till now we have 1 plus 3, 4. And in species balance equations, if we are coming, in the previous slide itself we have seen we have 4 species, that is carbon monoxide, H2O, CO2 and H2. So 4 species we have, but now how many number of species balance equations do we need to solve? We need to solve 4 minus 1, that is number of species minus 1 number of equations we need to be solving. Because the total, if we put one more, the total is already there in the continuity equation, so it is minus 1. So here we have 3 and one more energy conservation equation we have, which is adding up to 1. So here 4 and mass and momentum conservation we have 4. So on the whole it is 8 equations. Answer is option D. So we have continuity equation 1 equation, momentum conservation equation 3 equations, and energy conservation equations we have 1, and species conservation equations we have 4 species conservation equations. But how many do we need to solve? We need to solve only 3, ns minus 1. So 1 plus 3 plus 1 plus 3. So 1 plus 3, 4, 5 and 6, 7, 8. 8 equations we need to be solving. The answer to this particular problem is option D, that is 8. 8 is the right answer. We will go to question 5. In question 5, it is asked that the rate of reaction term appears in which of the following conservation equations? Options: species conservation equation, mixture mass conservation equation, mixture momentum conservation equation, mixture energy conservation equations. So what has the rate of reaction term, that is R, or something, how much concentration it is changing from inlet to outlet with respect to time. That term it is appearing in which of the following conservation equations. So mixture momentum conservation equations, if you remember the equations, we are not dealing with that, so that is not there. And mixture mass conservation equation, that is in the total continuity equation also, we are not dealing with the rate of reaction terms. The left out ones are 1 and 4, that is species conservation equations. We need to include this uh, rate of reaction term, and in mixture energy conservation equation also we need to include the rate of energy reaction term. So answer is option A 1 1D, option B it is 1 and 4, option C it is 2 and 3, option D it is 1 2 3 and 4. So 1 is right and 4 is right. So answer to this particular problem is 1 and 4. So answer is option B. We'll see what are the governing equations. So sorry, it should have been so the continuity equations, what is the equation we have in the vector form? Dou rho by dou t plus del dot rho u is equal to 0. Here we are not seeing any rate of reaction term. Similarly, for the momentum conservation equation, we have dou u by dou t plus del dot uu is equal to nu del dot del u plus g minus 1 by rho del p. So that is, we have divided the momentum conservation equations by rho. And now if you look at it, again we are not having any rate of reaction term. So again in momentum conservation or mixture momentum conservation equations, we are not dealing with any rate of reaction terms. So finally, energy conservation equations, we have it as this: dou t by dou t plus del dot ut is equal to k by rho cp del dot del t plus mu by rho cp phi b plus qr by rho cp. So here in the QR term, we would be getting the rate of reaction term. We'll see that in the next slide. And finally, in the species conservation equations, we have dou rho yi by dou t, that is yi for the mass fraction of that particular component I, that is CO, CO2 or something, and plus del dot rho u yi is equal to del dot gamma del yi plus Si. Here again in the source term, that is Si term, we would be having the rate of reaction terms. So we'll just see the chemical reaction. If some chemical reaction is happening inside a system, what is the equations we will be having? AR1J x1 plus AR2J x2. These are just coefficients and these are the reactants, giving A product 1 J x1 plus A product 2 J x2, like coefficients of the products. Okay, this should be different, just ignore it for now. I mean, this would be x1 x2 and like it would be giving out the products. So source term would be, what it would be, weighted fraction of product minus reactant into that particular component rate of reaction. So here again we have the rate of the reaction. And one more term what we saw in the energy balance equation or energy conservation equation is the QR. QR, what it is doing, rate of the reaction is coming over here, and it is minus APIJ minus ARIJ into delta HF. So that is the amount of heat generated is giving over here, and this rate of reaction is given by this equation, where Kf into, for each terms we are accounting for the products and the reactants, and the rate of reaction rates are expressed in terms of Arrhenius coefficients, in terms of activation energy and temperature exponent and a pre-exponential factor. So rate of reaction is expressed in terms of all these things. It is not directly accounted because we can calculate it from these values as well. Like that's why in previous question, which it is not explicitly required, but it is coming out in the form of Arrhenius coefficients, activation energy, temperature exponent and pre-exponential factors. So in the species balance equations and in the energy conservation equations, we have the rate of reaction terms. So we can calculate it, it is not directly required. That's what it is means. So that's all for this week's problem. Thank you. So in this week, what we saw is an introduction to the chemical reaction, handling through CFD by means of mass conservation and species conservation equations and energy conservation equations. In addition to that, we have seen few problems based on flow through a rectangular duct and how the conservation equations are changing. So when fluid flow alone is considered, we have seen in the first half, and in the second half we have seen when fluid flow is considered along with a chemical reaction, which is again taken which whose effect is taken by means of species conservation equation and the energy conservation equations. So that's it for this week's problem. If there is any doubts, please ask now. We can clear that. Yeah, thank you. Yeah, if there are no doubts, we can close the session actually. Thank you so much for joining. We'll again have next week class. Thank you. I'll just wait 2 more minutes. If there are no doubts, we can log off. Thank you. Yeah, thank you for joining. I'm just logging off now. Thank you.